Hello students, welcome back. Originally I planned section 3 as next week's topic, but I have plenty of time left, so let's talk about it a little bit. Let P be an odd prime and let P does not divide A. In other words, A is non-zero modulo P, as usual. We define the Legendre symbol A of P as +1 if A is a quadratic residue of P, and -1 if A is a non-residue of P. And then we use not just abuse of notation but abuse of terminology and call A and P as the numerator and the denominator of the Legendre symbol. I'll try not to use those kind of terms, too confusing. By the way, we have 1 or -1 for quadratic residue versus non-residue. Doesn't it remind you of something? In section 2 we went through this Euler criterion. For quadratic residue, this power is 1. A to the p minus 1 over 2 power is 1. In fact, that is either +1 or -1, and nothing else. Well, actually it could be 0, but that's special trivial case that we removed early on. So it's going to be a +1 for quadratic residue, -1 for non-residue. And that's precisely what you're looking at here. So you can consider this as a shorthand of A to the p minus 1 over 2 power, roughly speaking. But a little bit simpler, and that kind of simplification makes it easier to do some difficult computation from time to time, and I'll try to show you some examples like that. But before that, let's talk about some properties here. First, if A and B are congruent, then A over P and B over P are the same, and that's pretty clear because if A is a quadratic residue, then so is B and vice versa. A squared over P is always 1 because a square number is always a quadratic residue. And here, just Euler criterion, A to the p minus 1 over 2 power. And this one here, this one requires a bit of a work because there's no obvious way to see it except to get our hands dirty and actually doing it. So we have two characters A and B to consider and two outcomes, +1 or negative outcome. So +1 or -1 for A or B. So it's kind of like coin tossing. We have 1, 1, -1, -1, 1, -1, or -1, 1. Just like head, head, tail, tail, heads, tail, tail, head. And for each, calculate and then see if this multiplicative property works out. It works out in the end. 1 times 1 is 1, -1 times -1 is +1, 1 times -1 is -1, kind of like that. And this is the least obvious, but the most useful aspect of Legendre symbol, I would like to say. Next, 1 over P is always 1, and that's really duh. 1 squared is 1. -1 over P, well, it's the same as this Legendre symbol, except that we don't have to worry about congruence because -1 to whatever power is either 1 or -1. But if you want to prove, well, I can go ahead and provide you a proof. The proofs are left to students, I said, but actually I went through all the proofs, so there you go. So those are algebraic properties of Legendre symbols. And let's try to utilize those in actual problems. And here's a problem from our textbook. X squared plus 46 is congruent to 0 modulo 17. Does it have a solution? Or equivalently speaking, x squared is congruent to -46. Does it have a solution? That means whether -46 is a quadratic residue or not. That's something we have to find out. Is this a quadratic residue? One way to find out is, of course, to do it this way. -46 to the, let's see, 17 minus 1 over 2 power, and what is this? Negative 46 to the 8th power, isn't it? 16 over 2, and that's, well, you can do it this way, but even with calculator it's going to be hard. If you don't have calculator, you can't do it that way. One way to handle it is to use Legendre symbol like this. Negative 46 over 17 is same as negative 51 minus 46 over 17. 51 is 17 times 3, so that's congruent to 0. 51 minus 46 is 5, so basically we are looking at 5 over 17, and that's 5 to the 17 minus 1 over 2, so 5 to the 8th power. How do you do 5 to the 8th power computation? Suppose if we don't have calculator, and I can reduce like this, 25 to the 4th power, and 25 is congruent to 8. 25 minus 17 is 8, and 8 to the 4th power come down to 64 to the 2nd power, and then 64 is 68 minus 4, where 68 is 4 times 17, so that's actually congruent to 0. And negative 4 squared is 16, and that's congruent to negative 1 modulo 17. So we got negative 1, so there's no solution. Negative 46 is not a quadratic residue. This is another method. This one is from our textbook. Negative 46 over 17 and decompose into negative 1 over 17 times 46 over 17. And then negative 1 to the 8th power is 1. So this one actually becomes 1 and drops out. So we have 46 over 17. And that's congruent to 12 because 12 is, let's see, 46 is 34 plus 12. And 34 is 2 times 17, so that's actually 0, adding 0, so it doesn't change. And then 12 is 3 times 2 squared, and we can use this property to decompose 3/17 times 2/17 squared. Whenever squared, we have 1, because negative 1 squared is also positive 1. So we have 3/17, and that is 3 to the 8th power, 81 to the 2nd power, and 81 is 85 minus 1, which is 5 times 17, so this is actually 0. So negative 4 squared is negative 4 squared is positive 16, and that's negative 1 modulo 17. That's another way to do it, and this is textbook's way, and I did it this way, which is easier. I don't know, you choose. Me personally, of course, I like mine because I did it and then looked up the textbook, and textbook's methods was a little bit different. Okay, how about the next problem? Yes, I really wanted to show you this example because this really shows you real progress of this Legendre symbol. How useful is that? You can see. Let's see. You have to prove there exists a certain x in z, an integer such that x squared plus 1 is congruent to 0 mod p. Or if you flip this to the other side, you're going to get this expression, and that means negative 1 is a quadratic residue of p. If and only if the prime number p is 4k plus 1 type. Remember, there are two types of odd primes, 4k plus 1 type and 4k plus 3 type. Divide by 4, then the remainders are 0, 1, 2, or 3. Remainder 0 means it's composite, divisible by 4. Remainder 2, that means it's an even number, and there's only one even prime. That's 2. That's out of consideration here. For odd primes, either remainder 1 or remainder 3. 4k plus 1 type or 4k plus 3 type. Remember that? Remember that and apply Legendre symbol, then you can get an easy answer like this. We're going to find out whether negative 1 is a quadratic residue or not. We're going to prove this. Negative 1 over p is 1. Yeah? That's Legendre symbol. and then algebraic rules. Okay, negative 1 over p, how do you find it out? Negative 1 to the p minus 1 over 2 power. And here, p is 4k plus 1 or 4k plus 3. When p is 4k plus 1, then the first line applies. We have negative 1 to the even power, that's 1. 4k plus 3, then second line, negative 1 to the odd power, so we get negative 1. So, what do you have? Quadratic residue if and only if 4k plus 1 type, the first line. So that completes the problem for that completes the proof using Legendre symbol, and thanks to Legendre symbol the computation was very simple. And then quadratic residue idea and maybe Euler's criterion in any case. But what if you don't know that? In that case, you may have to do it hard way like this. A squared is congruent to negative 1 and apply Fermat's theorem. A to the p minus 1 power is 1, and then a squared to the p minus 1 over 2 power. So negative 1 to the p minus 1 over 2 power is positive 1. So this p minus 1 over 2 power has to be an even power so that you get positive 1. Now flip this denominator to the other side, you get p is 4k plus 1. So we have the proof for the one direction, the forward direction, using Fermat's theorem as I'm highlighting in blue. Compare that with Legendre theorem. Well, which is easier? I think this method is easier, but this wasn't too bad. Now, how about the opposite direction? Oh, this is bad. We are using Wilson's theorem this time. Let's see. pk plus 1, so p minus 1 is 4k, so divide by 2. We still have an even number, remember that. And then apply Wilson's theorem. P minus 1 factorial is congruent to negative 1. And then p minus 1 is congruent to negative 1. Yeah, p is 0. P minus 1 is congruent to negative 2 because p is 0. And p minus 3 is congruent to negative 3 and so on. And the last one, p plus 1 over 2 is congruent to negative of p minus 1 over 2. You can easily check. If you add them up, you get 2p over 2, so p, that's 0. So what do I get? We just got a repetition of all those multiplication of the latter part with sign changes. Negative 1, another negative 1. How many negative 1s out there? There are this many because there are this many factors. And then this part multiplied twice. So we get p minus 1 over 2 factorial squared. But then again, this one read, negative 1 to the p minus 1 over 2 power is assumed to be 1. Not assumed to be 1, excuse me, is 1 because p minus 1 over 2 power is an even number, which came from p is 4k plus 1. So that's positive 1. So what do you get? Negative 1 is this factorial squared. So putting a as that factorial, we have a solution. A squared plus 1 is congruent to 0. So we can prove it like this. Fermat's theorem in one direction and Wilson's theorem in the other direction. But then again, do you really want to prove it this way? Or this way? Well, I think I made my point. This is one of the reasons that we are studying Legendre symbol to begin with. We can make enormously complicated computation into something much simpler using Legendre symbol. Yeah, okay, we can do something really similar with Euler's criterion as well, but you'll see Legendre symbol is even more useful than that.